Next, we'll look at minimization problems that not only have equality constraints as they did in the last video, but also inequality constraints of the form h of x is less than or equal to 0. For example, let's take the same problem as we had in the last video, but add an inequality constraint x1 greater than or equal to 0. And since this is not in the form h of x less than or equal to 0, we'll switch it and write minus x1 less than or equal to 0 so that it's in the standard form. So I would suggest that you pause the video at this point and from the graphical construction of the last video, see if you can figure out a solution to this problem with the new inequality constraint. Now, just as we did in the last video, we have a recipe for these inequality constraint problems. Again, we formulate a Lagrangian, but this time we also include a second, the inequality constraint in the Lagrangian, lambda times minus x1. And lambda is a new Lagrange multiplier corresponding to the inequality constraint. The second step is again setting the gradient of the Lagrangian equal to 0. The third step is writing down the constraints. There is now a fourth step with the inequality constraints that says that lambda, the Lagrange multiplier corresponding to the inequality constraints, is greater than or equal to 0, and the product of the Lagrange multiplier and the inequality constraint is equal to 0. What this means is either the constraint is 0 or the multiplier is 0. Both cannot simultaneously be non-zero. Now these conditions are called the Karush-Kuhn-Tucker conditions, or KKT conditions, after the mathematicians who formulated them. Again, these are necessary conditions, and we don't again discuss sufficient conditions because they're more complicated for the the constraint case. But if we use, for example, solvers in MATLAB, they would seek minimizers. So we kind of skip the discussion of sufficient conditions. So applying these KKT conditions to our example, first we calculate the gradient of the Lagrangian. We get this, and that gives us the two equations: 3 plus 2 mu x1 minus lambda equal to 0, and 4 plus 2 mu x2 equals 0. Then we write the constraints, the equality constraint and the inequality constraint. Then we have these conditions that for the inequality Lagrange multipliers, lambda is greater than or equal to 0, and the product lambda times minus x1 equals 0. So we solve this by trial and error. First we try lambda equals 0. This we know doesn't work because lambda equals 0 is the situation in the last video, and that won't work because now we have the additional inequality constraint. So if lambda is not equal to 0, the fourth KKT condition tells us that x1 must be 0. So let's try that, and then we get actually two solutions, and one of those solutions is the minimizer. So if we take the MATLAB code we had in the last video, we can easily modify it to include the inequality constraint. There are many ways with fmincon to include inequality constraints. Here we do so with by introducing a lower bound of 0 on x1, and we can calculate the corresponding Lagrange multiplier by simply doing lambda dot lower. Now there are some interesting special cases of inequality constraint minimization problems. The first is this: minimize f transpose x. Here f is a vector of the same length as same size as x, with equality constraint a equality times x equals b equality, and then inequality constraint ax less than or equal to b. Here we see that the objective function and both the constraints are all linear in x. This kind of special case is called a linear program, and MATLAB has a solver called linprog to solve this kind of special constraint minimization problem. A second special case is where the objective function is of the form 1/2 x transpose h times x. H, the matrix H is called H because it's the first letter of the word Hessian. Subject to again a equality x equals b equality and ax less than or equal to b. So here the objective function is quadratic in x because x transposed h times x is kind of like x squared, but the constraints are linear in x. This kind of a special case is called a quadratic program, and in MATLAB there's a solver called quadprog that solves this kind of problem.